this video on intervals of increasing and decreasing and the first derivative test is meant for Mrs. Rose's AB calculus class. Alright, let's jump straight into it. We want to be able to find intervals where f of x is increasing and decreasing. To start off, the very first thing that we're going to do is locate the critical values of the f of x. By now we're all getting pretty good at this, so we're going to take the derivative of f of x, 3x squared plus 6x, and set that equal to 0. When you solve for x, let's factor out the GCF, and then our two critical values are 0 and -2. The next thing we're going to do is use the critical values to set up test intervals. Just use critical values to set up intervals. When you're writing your intervals, you're going to start with -infinity and break it up at your first critical value on the number line. So since -2 is less than 0 on that number line, it's going to come first. So we're going to break it up at -2 first, and then from -2 to 0, and then from 0 to infinity. The next thing we're going to do is determine the sign of f prime of x at a test value in each of the intervals. So a good test value from -infinity to -2 might be something like -3. A good test value between -2 and 0 might be -1. And a good test value between 0 and infinity might be 1. So if we're looking for the sign of f prime of x at these values, we're going to plug in -3 first into our derivative. So doing some scratch work on the side, I can do something like 3 times -3 times -3 plus 2. So this is going to be -9, this is going to be -1, this is going to be +9. So the only thing I'm really interested in is the sign. Since this is positive, I'm going to write a plus right here. When I do the sign of f prime of x at -1, I'm going to use the same derivative, 3 times -1 for 3x, and then -1 plus 2. So I'm going to get -3 times +1, which is -3. So again, all I'm interested in is the sign, which is negative. Finally, when I plug in the last one, I'm going to get 3 times 1 times 1 plus 2, and that's going to be 3 times 3, which again is 9. And all I'm really interested in is the sign of the derivative, so that's going to be positive. The next thing we're going to do is determine whether f of x is increasing or decreasing on each interval. I've rewritten the work in a more chart-like form with our intervals, our test values, our sign of the derivative, and then finally we're going to determine on the interval where if it's increasing or decreasing. If the slope is positive, we say that f of x is increasing. If the slope is negative, then we say that f of x is decreasing. And again, when the sign is positive, f of x is increasing. So our original question asked us state the intervals where the function is increasing and decreasing, and now we're using calculus to do that. So we say f of x is increasing on the interval from negative infinity to negative 2, decreasing from negative 2 to 0, and it's increasing on the interval from 0 to infinity. Okay. The first derivative test uses what we just did, using intervals of increasing and decreasing, to talk about relative extrema. Okay, so we're going to let c be a critical number of a function, f of x, that is, the function is continuous and differentiable on an interval, except for possibly when x is that critical value. If the sign of f of x changes from positive to negative at that critical value, then f of x has a relative maximum at that critical value. So if you have a quadratic, for example, it's inverted, and here's your critical value, then if your slope was positive and changes to negative, and then right here it's 0, then we're going to have a relative max. On the example that we did previously, we have a change from positive to negative right here at x equals negative 2. So since x equals negative 2 is a critical value, critical number, and f prime of x changes from positive to negative, then x equals negative 2 is, or I guess I should say the point. So the y value is 8, the point is negative 2, 8, is a relative max. Okay, continuing with that first derivative test, if you have a critical value and the derivative sign changes from negative to positive at that critical value, then we have a relative minimum. So we have a parabola, we have a critical value, the slope changes from negative to positive. So of course here we have a relative minimum. On our problem over here, at 0, oh goodness, at 0, the slope changes from negative to positive. So we have x equals 0 is a critical number. F prime of x changes from negative to positive. Therefore, the point 0, 4 is a relative minimum. Okay. Finally, with our first derivative test, if we don't have a change, if there's no change in the slope sign at the critical value, then there is neither a relative maximum or a relative minimum. That can look like a cubic, positive or negative. The slope is negative on both of these, the slope is positive on both of these. Okay, now let's look at one that doesn't have a function, we just have a graph. We want to look at critical values of this graph of f of x. We know that critical values happen whenever the slope is 0 or is undefined. So we can see that we have a horizontal tangent line at x equals 1 and x equals 3. So our critical numbers are there. we're going to use those critical numbers to create intervals. If you have 2 critical values, you're going to have 3 intervals. If you have 3 critical values, you're going to have 4 intervals. But your intervals should be broken up everywhere that you have a critical value. The next thing we're going to look at is the sign of the derivative. Obviously, if we have a graph instead of a function, then we don't have to worry about a test value. You can just look at the slope of the line on each interval. So from -infinity to 1, this function is increasing, so we have a plus, decreasing from 1 to 3, and increasing from 3 to infinity. So this is really easy to decide where the function is increasing and decreasing. This function is increasing from -infinity to 1 and from 3 to infinity. This function is decreasing from 1 to 3, and we know that at 1 we have a relative max, and at 1 we have a relative min. Now this example was very easy. We could have done this in Algebra 2, just looking at the graph. However, we're going to apply this to a much harder example when we have the graph of f prime of x. This is exactly the same graph, but we're looking at it very differently when it's the graph of the derivative. Here, when we're looking at critical values, we're looking at where the derivative equals 0. If this is the graph of the derivative, that's going to equal 0 whenever it crosses the x-axis. So when we go to do our test intervals, we're going to break it up and have 4 intervals since we have 3 critical values. From -infinity to 0, from 0 to 2, from 2 to 4, from 4 to infinity. Again, we have a graph, so there's no reason to get a test value, but what we're looking for is the sign of f prime of x. From -infinity to 0, we're talking about this piece right here. So since this is the graph of f prime of x, that piece is below the x-axis. The graph of f prime of x is below the x-axis. So the sign of f prime of x is negative. The sign between 0 and 2, all of this is above the x-axis, so all of the values are positive. Between 2 and 4, all of these y values, which these are values of f prime of x, all of them are below the x-axis and therefore negative. From 4 to infinity, they're all above the x-axis, they're all positive. So when we go to make our conclusions, we know that f of x is decreasing on the interval where the slope is negative. So from -infinity to 0 and from 2 to 4. Likewise, we know that the function is increasing on the other 2 intervals. We can also make conclusion statements about relative extrema. We know that f of x has a relative minimum anywhere that the slope changes from negative to positive. So we're going to have a relative min here and a relative min here. So at the point 2, I'll work out the y value in a second, and at 4 something. Oops, I made a mistake. We don't have the original function, so we have no idea what those y values are. So we just say at x equals 0 and at x equals 4. All right, we also know information about where we have a relative maximum. So our relative maximum is going to occur anywhere that the slope changes from positive to negative, and that's going to be at x equals 2. All right, back to functions. So intervals where it's increasing and decreasing, we want to find critical values. So we're going to take our derivative first. 1/2 minus cosine x and set that equal to 0, as we do whenever we do any critical values. Add cosine to both sides, and we're looking for what angles on the unit circle are going to give us a cosine of 1/2. Those two angles are pi over 3 and 5 pi over 3. So our test intervals on the interval from 0 to 2 pi, we're going to start at 0 and go to pi over 3, go from pi over 3 to 5 pi over 3, and then from 5 pi over 3 to 2 pi. We don't go to infinity and negative infinity because of our interval. The next thing we're going to do is look at a test value. On the interval from 0 to pi over 3, we don't have very many options, but we should use a reference angle. I'm going to use pi over 4. Between pi over 3 and 5 pi over 3, I'm going to use pi, but you can pick any angle. And between 5 pi over 3 and 2 pi, I'm going to pick 7 pi over 4. Now we're looking for the sign of f prime. When you plug in pi over 4 into your derivative, you're going to get a negative, then a positive, then a negative. So then we can make several concluding statements. We know that f of x is decreasing on the interval from 0 to pi over 3 and 5 pi over 3 to 2 pi, and f of x is increasing on the interval from pi over 3 to 5 pi over 3. We know that f of x has a relative min at the point pi over 3, and the y value for that is complicated. It's pi minus 3 square roots of 3 all over 6. And then we know that f of x has a relative max at 5 pi over 3. And again, that's because the sign changes from positive to negative, and the y value for that is 5 pi plus 3 square roots of 3 all over 6. For 2 more examples, check out the notes slides on Edline here and here. And finally, one last thing, vocabulary for the chapter, for the problems in the book. The word monotonic means either always increasing for the entire interval or always decreasing for the entire interval.